All right, we have the wonderkind himself coming up, someone who data sovereignty and ownership, returning the user to the center of the process for networks. This is Ty Everett. Welcome.
All right. Clicker anywhere? Let's see. Thank you. All right, everybody. Talking about some new things today. So, Bitcoin for a long time has been limited in one important way. We have scripts. These scripts are predicates. And when you want to actually go beyond that, there's some challenges. So what I'm going to be doing in this presentation is I'm going to be walking you through some of the technical breakthroughs that I have come across with my team as we have been talking about building a general purpose CPU that uses the Bitcoin UTXO architecture. As part of this, I've developed my own instruction set architecture and assembly language for this new CPU, and it utilizes UTXOs to perform multi-stage computation, including recursion, subroutines, loops, and the ability to compile higher level programming languages such as C, C++, eventually even things like Java, JavaScript, Python, down so that you can express things within Bitcoin, interacting with the capabilities that the blockchain provides. So firstly, I'm going to talk about some of the difficulties with multi-stage computation. And then I'm going to cover kind of how we've been able to overcome those difficulties. I will provide some examples. And then I'll get into the architecture of the CPU itself. We'll walk through how it works. And then at the end, we'll go through some of the implications, use cases, and applications of this new technology. And if there's time, which I'm not sure, I will answer questions. So first up, when we are in Bitcoin, we have scripts on outputs. In Bitcoin, transactions exist. They are the fundamental way that we interact with the blockchain. There are inputs and there are outputs. The outputs have predicates, which are a particular type of a lock, in this case, to kind of secure our coins and make sure that nobody can run off with them without our permission. And they set up all of the rules under which we evaluate the, kind of the potential people who try to unlock our coins and use them. There can be many ways to unlock a particular output. Outputs in Bitcoin are what represent tokens. So things that represent real things of value, right? A token is something that represents something of value, and they're represented with outputs. And so you can set up some basic constraints within these outputs. Things like even enforcing constraints on what the next transaction can be. So that's known as stateful UTXOs or stateful smart contracts that have a state that persists over time. However, it's challenging to have contracts that have open-ended, undefined number of future sequences. I'm not activating this yet, so I'll go to the next thing. But I was still just kind of covering some groundwork here. Essentially, what we're talking about here is these outputs and the constraints that can be applied to them. Right now, if you want to set up an unbounded set of, if you want to allow the person who's solving your smart contract to describe the solution to whatever problem you propose across multiple transactions, multiple spends, there are problems with that, right? Because if, say, Alice creates a smart contract that has an output, and then Bob wants to describe the answer or the solution that unlocks that smart contract across multiple spends, it's a problem. The reason why that's a problem is because, well, Bob could broadcast a malicious partial solution. And what that means is that the UTXO, the output that Alice created for her smart contract, has been corrupted. And so if there's a partial solution, then, well, you can't actually get to the real one if you make some missteps. So let's jump into an example. So suppose we have Alice who is going to propose a new contract as an output in a transaction, which is how you propose all contracts in Bitcoin. You have some output that describes the constraints under which the puzzle can eventually be unlocked across, one transaction or multiple once it kind of releases itself. And suppose Bob comes along and he's going to offer the solution. So he's going to start describing his multi-stage solution across multiple transactions. So transaction 1, transaction 2, step, 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 right? We go through and we put in the right information across each of the different parts of the transaction, or each of the different parts of the solution, which can be described in this case across multiple transactions. However, what if Bob makes a wrong step? Well, he's broadcasting these transactions out to the network, and now there's a UTXO that Alice created that is now kind of in an untenable state. We can't use it, and so everything is locked up and a little bit broken, and that's not good. That's the fundamental problem with describing multi-stage computation on Bitcoin, and thereby allowing us to eventually achieve general purpose computation on top of Bitcoin, which is something I'll get to. But as of right now, we have this wrong step made by Bob, and the UTXO is locked. Nobody can use it. And so, maybe the answer is that if Bob hasn't actually found the solution, then he shouldn't broadcast the transactions, right? And that would solve the problem. Except what if Bob was evil? What if Bob was just going to try to lock up every UTXO created by every person who is trying to just get solutions to their problems? That's going to be a little bit difficult for everybody, isn't it? Nothing's going to work. You're not going to be able to describe things. The entire world is broken. This is Armageddon. We should cancel the London Blockchain Convention because we're all just... No, there is a better way. We have a solution to this. And our solution involves a thing called a solver's bond, a state reset, and a time lock. We can combine them together, and we'll describe how that works in a second. So, when Bob goes to solve Alice's contract, Bob is actually going to put in a little bit of his own money and put up a bond. So he's kind of collateralized into the system. That's the first step. Then a timer starts. So he has a certain amount of time to actually arrive at his solution. And if he does not arrive at the solution within the amount of time specified, then we've actually recorded an original copy of the initial state of the UTXO prior to Bob's involvement. And after that time has expired, we can go back and we can reset the state of the UTXO back to the way it was, and anybody can do this before Bob was involved. Now, those transactions, that record of Bob's failed attempt to broadcast a multi-stage contract solution, is recorded on chain still. But now, number one, Bob loses his bounty. And number two, anybody else has a stronger incentive to come along and attempt their own solution. So what this does is it allows us to reset the state of UTXOs and achieve a world where we can have multi-stage contracts on Bitcoin. So that's the initial part of the solution. So, that's the initial thing. Let's have an example. So, like we had before, someone's going to get started, and Alice is going to propose a contract. Bob is going to post his bond this time. The timer is going to start. And then Bob is going to attempt his solution. Now, either one of two things is going to happen at this point. Bob's solution is going to satisfy all of the multi-stage constraints across many transactions that eventually unlocks the UTXO or achieves some state checkpoint, at which point he is kind of in the clear, or he's not. So is Bob's solution valid? Well, if so, everybody is happy. But if not, then eventually that UTXO is locked. Nobody can do anything with it, right? We saw those padlocks before. Well, eventually that timer is going to expire. And then someone is going to come along and reset the state of the UTXO back to how it was before Bob was involved, only now Bob has lost his money, and Carol, some other individual in this equation, can come along with a higher bounty and attempt the same solution. And this will continue indefinitely until the checkpoint is reached or the ultimate UTXO is consumed and broken down. So in this way, we can achieve multi-stage computation. And that's our example. So there we go. Everything's all good, guys. We don't have to worry. No Armageddon. We can bring back all the things we're doing, and we can actually do some cool things. So this is a cool theoretical idea, but I want to talk for a second about how we can do it. Kind of, what are some real-world applications here, right? Like, what is this useful for? Well, I talked about multi-stage computation within the context of a single solver and a single person who is proposing a contract. It allows unbounded loops, of course, things like that, right? The number of transactions in your ultimate chain does not need to be part of the original UTXO. You don't need to have to know that ahead of time. But you can also do things like real-time data sources from signed oracles. So you can have contracts that, while they're being worked on in real time, incorporate things like oracles that sign things like the weather, and that changes over time. And the rules of the system in which you are operating, the UTXO, the constraints that govern it, can be updated dynamically as solutions are being proposed and as new people are maybe providing different data sources for those solvers for lots of things. Real-time data sources, really useful. Next up, if you don't know how many loop iterations you are going to need in your solution, well, this is the thing for you, because just get to the checkpoint and you don't lose your bounty. Very simple. Custom and dynamic algorithms. So I'm going to talk about in a second how the CPU works and implements this into an actual instruction set architecture and assembly language and how we can build on top. But basically, if you have done anything with early computers, you'll know about peek and poke and this idea that you have the ability to write things into memory and then actually, as part of your program, accept user input, code, like type in things into memory, and then jump to that location and dynamically execute custom algorithms as part of the evaluation of whether the solution is valid and subject to other constraints. So a little bit more complicated than it sounds like, but that's fine. Also, if you want to code up a simulated world in which, like a game world, for example, or some simplified model of the real world that could even be extrapolated back onto the real world, things like a simulated postal network where you're trying to simulate all of the packages and all of the trucks on the road and delivering them to people. It's a lot easier when you don't have to code the entire thing in a single UTXO with a single predicate. Just saying. So there is one final class of people who think this is useful, and those are the ones here who think it would be fun to implement a CPU architecture that does general purpose computation and just see what people build with it. So what do you say we jump into the Bitcoin CPU and how it works? Instruction set architecture here. The CPU has 4 registers. It has a stack, and it has a heap. There are various opcodes. It's got a base pointer and an execution pointer and a stack pointer like any CPU. It's coded up in script, and it supports things like JSR, RSR instructions in assembly, so you can do things like recursive subroutine calls. I implemented a Fibonacci counter as a demo. You can check it out on the GitHub, which there's a QR code at the end. Yeah, you've got a lot of different things that are here, but so every transaction is a clock pulse, meaning that you can execute 1 opcode per transaction. Currently, I might add multi-opcode per transaction support in a future version if we can optimize it. But those are the fundamentals. So here it is. This is, if anyone has done things with CPUs, this is on the left, you have the heap, which is where your program code is being executed. On the right, you have a stack. And in the middle, here are representations of each of the 4 registers, the general purpose registers, and then, of course, you have your stack pointer and heap execution pointer. And then, of course, I've omitted a few things like the base pointer and the call stack for simplicity. But let's take it for a spin. So I'll set up the execution pointer, which generally starts at 0, although you can start it wherever you want when you initialize your UTXO. And then we'll set up the stack pointer. And so someone's going to create, on the bottom here, these are going to be transactions that are actually executing the different clock pulses of our CPU. So transaction 0, Alice has written this program on the left in the heap and has defined some rules that have to be done. There's a lot of opcodes for like data input output, all the opcodes you could expect from a rich ISA, such as arithmetic and logic and all that stuff. But anyways, you write your code in assembly or some higher level languages that compiles down to assembly, and then someone comes along and they're going to start to solve it. So transaction 0 is when Bob says, oh, I think I can broadcast the whole chain and kind of get to the checkpoint or get to the terminating opcode, which is called opwin. So we have opwin, which is like, okay, well, we're done. We're going to let you unlock the whole UTXO. And there's some new opcodes we'll get to in a second. But yeah, Bob puts up his bounty, starts the timer, and then starts executing clock cycles. So you can see here, as we do, execution pointer moves forward and various opcodes happen. And then eventually we're going to get to a conditional jump. So jumps on Bitcoin, right? People say you can't do loops on Bitcoin. They say you can't do jumps on Bitcoin. These are all transactions at the bottom, and I've color-coded them. And so we're going to get to our first jump. So ready for this, guys? There's a jump on Bitcoin. There you go. So yeah, you can see that one's yellow, and now we're back up here. So there was some condition that was met, and we jumped back up to the top rather than getting to the green, opwin it's called at the bottom, where I've actually terminated the program. So run another loop, right? And there you have it again. We just done another loop in Bitcoin. Now the thing is, when you want to have Bitcoin be Turing complete, as someone told some other people back in 2015, you have multiple transactions, and that's what we're doing here. So we'll go ahead and run another iteration of the loop. And finally, you can see that we've actually gotten past it. And so once you get to the green one, opwin has been executed. The program has been terminated. The UTXO is released. The winner gets to have their solver's bond back. So they get their money back, of course, because they found the solution. They successfully got to the checkpoint. And then CPU powers down and they get their money. So execution is successful. That's how the CPU works at a high level. That is with a basic program. A little bit simplified, but you can check out the code, and happy to answer a lot of questions about it if you so inclined. So would you guys like a side of opcodes with that? Firstly, opwin, as I described, it's relatively simple. Oh, where am I? Have I lost? Oh yeah, so yeah, here's some opcodes, right? We got opwin, which is when you actually want to terminate. So you write opwin as part of your assembly code or some high-level language. You could have some like new keyword that we could just add so that it compiles down to opwin in assembly. Oplose means you just can't do anything else. It's like halt. And keep in mind, if you halt the CPU, that timer is going to expire. Someone's going to come along and reset the state of the heap and the stack and the pointers and everything back. And then someone's going to start over, and they're going to get to that solution eventually. We got opbill and oppay. So as part of this, we can actually put constraints on the transaction tape. So I say transaction tape, which is the long chain of transactions that we're using to describe our solutions to general purpose computation in this context. And we can require that in opbill, some other input is added alongside the CPU tape input that adds additional money of a particular amount, as defined in register 1, into the value of the contract. So that if you're going to take this path of execution in your code, you can actually add money to the system. And oppay, so because back in the day, Shatters was good enough to advocate we added 750,000 character long, big nums into script and enabled that. You can put an entire output script into a register, and you can put the amount of money you want in that output script, and then into another register. And then opPay forces the transaction that incorporates opPay to actually create that script and actually pay that person for work done, and then continue execution after that. So you can pay out of the system as well. Checkpoint. I talked about state resets, right? And I said you could reset back to the initial state. Well, it turns out you can also reset back to a checkpoint so that people can actually update things. So opWin, the way it works, it's very simple. We'll boot up the CPU again, right? Set up our pointers and start executing code. And eventually, you get to, so you can see some transactions happening there at the bottom. And eventually we'll get to opWin, and off you go. You win. So multi-transaction chain, however you got there, whatever other opcodes you had to execute, whatever input, you have like opread, which means that you can actually read user input from the transaction tape or from that point, and you can hook whatever I/O devices you want up to it. You can do memory mapped I/O as well, which is kind of cool. You have opload and opstore, things like that. Anyways, that's opWin. Oplose. Let's run through this. Let's actually think through how this applies all the way back to the original description of the solution we made to state resets, solvers, bonds, and timers. So we're going to execute an oplose. Someone's about to lose because there's a conditional jump, and they're not going to meet the condition, meaning they're going to fall through, and they're going to execute oplose. They couldn't clear the hurdle. So let's just show that. Once again, transactions are being executed at the bottom, and this person's hitting the conditional jump, but the condition's false, so they lose. Well, what's going to happen then? Anybody want to shout it out? What do you think is going to happen? Right, CPU terminates, nobody can do anything, so nothing happens. And that's going to force the time to expire. And someone's going to come along, because after the time expires, anybody can reset state. And now we're back up to the top. You can see the pointer just jumped back up to the top. Whatever was on the heap and the stack and the registers would be reset back to their original values. And right, new solver is going to come into the equation. They're going to pay a new bond. Mind you, now the old solver just lost their money, so better incentive to try again and get it right this time, right? Don't broadcast. Guys, work off chain. Don't broadcast things if you're going to lose. It's not a smart idea. Let's go ahead and execute another one, right? So someone comes along and they say they aren't going to lose this time. So they actually jump past the oplose. They clear the hurdle. In this example, we've got transactions coming in once again at the bottom. You can see the arrows and how it connects. I just jumped over oplose. This was 162 slides, by the way. And at the end, you actually win. So now that person gets all of that money. So that's oplose in detail. And the final one I want to run through is really cool. It's actually something I'm really excited about, because you can do so much with all of this, but with this in particular is bill and pay. So suppose we're in some arbitrary, unimportant place in a program, and we're about to run, a couple of opcodes, and just, see on the bottom, we're just executing transactions, going about our merry day, and eventually we get to opbill. Well, these are transactions, and they spend each other. These are UTXOs, and so as part of opbill, I'm going to require that some additional input is funding that transaction, adding value to the new UTXO, and introducing more funds into the system from somebody who's paying for some service or something, right? Whoever's solving this problem must have decided that this was the most efficient solution, and that as part of that, some money should be introduced so that it can be later paid to some service provider for some action being performed. So just execute some more opcodes. You could jump around, make a few recursive calls if you want, compute some Fibonacci numbers if it's what you want to do. And then eventually you get another thing called opPay. So this one, it's just the opposite. We require some output be sent, and as part of that transaction, you can actually push onto one of the registers the script that you want in your output, and then you can keep going. So pay some person for some service, and then we just keep going about our merry way and just, execute more transactions. So that's how that works. It's really cool, guys. I'm so excited to see what everyone's going to build with this, because now we can do general purpose computation on top of Bitcoin, which we've needed to have for so long. And that, it's implications and future stuff. Okay. Testing my memory here from these slides. Okay, I can remember a little bit. Okay, unlimited, right. So this is a really cool computer for a few reasons. Because these things, this heap and this stack are stored off-chain, but the Merkle root of the hashed set that is the heap and the stack are stored on-chain, it means that you can have an unlimited amount of memory in your computer, as long as you can give it to the person, and you can also selectively disclose particular regions of memory privately to only solvers who have a need to know. And everything else is off-chain. So we're using hashed sets and doing it that way. As I alluded to earlier, with pushing an entire output script into a CPU register, memory elements are dynamically sized. So put a whole string in there, put 52 factorial in there. I don't know why I like reading factorials, but it was really cool. And I saw it run the first time. I was like, oh gosh, I know that's actually 52 factorial. So I was like, yes, this is correct. Anyways, yeah, we have the ability to dynamically size memory elements, and anyone can set up whatever memory mapped I/O they want. So that way, someone can, yes, it can run Doom, right? And yeah, we've got a new assembly language. I'll show you an example program here in just a second. Made a new instruction set architecture that has those new opcodes. That's why I had to make a new one. When is the last time we've actually really super duper needed a new CPU instruction set architecture with new opcodes? Because now we have the ability to pay people and stuff. So that's cool. Anyways, yeah, you're gonna be able to compile other things to it as well. This is an assembly language program using the new assembly language, and yeah, it's pretty cool. If you don't happen to know assembly language, here's a small detail about this program. You can ignore that if you want. You don't have to pay attention to it. Like I said, just yeah, don't 4 million Bitcoins if you say Bitcoin's not Turing complete. This is a really cool computer. It might be the coolest computer ever. I don't know. We'll see what we can do with it. I think everybody in this room could build some fun things. We should like have a hackathon or something. I don't know. Okay, so let me figure out where I am here. Right, we've got so use cases. Adaptive routing in logistics. You can create a simulated world in a higher level language that compiles down to this and makes this transaction tape. And you can simulate postal networks. You can simulate every type of network and solve, any type of problem with those, and incorporate, like I said, real-time data. So you can broadcast part of the solution, hit a checkpoint, wait for the oracle, broadcast the next part, hit a checkpoint, wait for the oracle. The program can check digital signatures. I added like op check datasig kind of thing using the Xiaowei, the implementation that was in script of ECDSA within script to actually verify a signature. But it made the CPU like 8 megabytes per transaction. So that's pretty big, but like right now it's 2 megabytes per transaction. So it added like a whole bunch. So I removed it temporarily, but we can add that back if people want to have like signed oracles and things. We're gonna have to optimize the heck out of this, guys, but yeah, you can do things like in the financial industry, you could incorporate signals from the market and different data sources so that you can do things like dynamic portfolio rebalancing, and you can manage digital assets using, obviously, you have access to the whole transaction pre-image. You can check how particular tokens are being managed and create complex constraints that govern things like tokenized CBDCs and things like that. Combining with our Babbage identity solution, you can do a lot with certificates and linked identity, type 42 stuff. Recommend checking that out. But you know, in a general purpose way, you can be dynamic about what you want to do. And let's see, yeah, you got some other thing. Real-time data sources, right? I mentioned that. Okay, what's next? So we think this is really cool, the breakthrough with respect to state reset and whatnot. And there's some fun things that we can do on top of it. I think this is more than just a CPU, because in the world, there are things called ASICs, or application-specific integrated circuits, and they're more efficient sometimes in terms of script size. I did write one that uses the same approach, and share more about that in 2025. Yeah, it's more than just a CPU, and there's a lot of different things that people can do. Yeah, we want to see compilers for other languages on top of this, and we want to see people use it for a lot of things. And we also want to make the scripts a little smaller. I heard from, I actually spoke with Craig Wright just a couple days ago, and he says, well, you can use hash chains and make it even more efficient, because of course he would say that. So anyways, in closing, we said a million transactions a second would be really cool, but that's only a 1 megahertz CPU, guys. We need to do more. We need to scale beyond 1 million transactions per second, and orders and orders of magnitude beyond. And we're going to. Yes, you can optimize some of this, and it's going to require less transactions than 1 per opcode if you want to optimize. However, there is a case for generalization, and there's a reason why we don't all have a whole bunch of ASICs running our computers, except for those little things called GPUs. But those came a little bit later. So yeah, we are going to need to scale this network. It is the only network capable of it. And now we can do general purpose computation with UTXOs. Bitcoin is Turing complete. Thank you. Happy to answer any questions.
We'll do some questions in the network and stuff.
Sure.
All right, we are right at time. So, but you are welcome to connect with Ty and learn more about Project Babbage during our networking session, which will follow our presentations. We will have a brief bathroom break right now.